Most of the time, the world around us makes perfect sense. You flip a switch and the light comes on. You drop your keys and they fall to the ground. You close your eyes and the world is still there when you open them again. Cause and effect. Action and reaction. A universe that follows predictable patterns, where one thing leads naturally to another. This is the world we know, the world we can trust. But then you start learning about quantum mechanics, and everything changes. You hear about particles that exist in multiple places simultaneously. About experiments where measuring something now seems to affect what happened in the past. About objects whose properties can somehow separate and drift apart. About realities that might be different for different observers, even though they're looking at the exact same event. And at first, you think maybe it's just the math. Maybe it's just equations being weird, abstractions that don't really mean anything in the real world. Then you dig deeper and realize these aren't just mathematical curiosities. These are actual experiments that have been performed hundreds, even thousands of times in laboratories around the world. They've been verified, refined, and tested under every condition scientists can think of. And the results never change. The weirdness is real. Not because we haven't measured carefully enough, or because our instruments aren't precise enough, but because this is genuinely how the universe behaves at its most fundamental level. That's what this exploration is about. Not the surface-level strangeness that gets mentioned in passing, not the pop science version of quantum mechanics that makes everything sound magical and mysterious without explanation. We're going deeper than that. We're looking at the real paradoxes, the ones that have stood for decades or even a century, the ones that still don't have universally accepted answers. These are the problems that keep theoretical physicists awake at night, the questions that divide the scientific community into competing camps, the puzzles that suggest our entire understanding of reality might need to be rebuilt from the ground up. When most people hear the word paradox, they think of brain teasers or logical puzzles. Something clever that twists your mind but ultimately has an answer if you think about it long enough. But quantum paradoxes are fundamentally different. They're not puzzles with hidden solutions. They're signposts pointing to places where our understanding of the universe completely breaks down. They're cracks in the foundation of physics itself. In the classical world, the world of everyday experience, everything makes intuitive sense. If you throw a baseball, it follows a predictable arc. You might not be able to calculate exactly where it will land without knowing things like wind speed, air resistance, the exact force of your throw, and the rotation of the ball. But in principle, all that information exists. The ball has a definite position at every moment. It has a specific velocity. It exists in a particular state, and if you had perfect information about all the variables, you could predict its trajectory with perfect accuracy. This is the universe that Isaac Newton described. A clockwork universe where everything operates according to fixed laws, where every effect has a cause, where the future is determined by the present, where objects have properties whether we're looking at them or not. Albert Einstein expanded this picture with relativity, showing that space and time are connected, that gravity bends space-time itself, that the universe is far stranger than Newton imagined. But even Einstein's universe, as weird as it got with time dilation and curved space, still made logical sense. It was deterministic. It was causal. It was real. Then came quantum mechanics, and everything changed. Scientists studying the behavior of atoms and subatomic particles began noticing things that shouldn't be possible. Particles that seemed to be in multiple states at once. Experiments where the act of observation changed the outcome in ways that couldn't be explained by simple disturbance. Connections between particles that persisted across vast distances with no signal passing between them. It wasn't that the measurements were imprecise or that the theories were incomplete. the universe itself seemed to operate by different rules at the quantum scale. The theory that emerged from this confusion, quantum mechanics, is perhaps the most successful scientific theory ever created. Its predictions have been confirmed to an extraordinary degree of precision. It explains the behavior of atoms, molecules, and fundamental particles with incredible accuracy. It's the foundation of modern technology. Every computer chip, every laser, every LED, every piece of electronics relies on quantum mechanics. GPS satellites need quantum theory to work correctly. MRI machines use quantum principles to peer inside the human body. The entire field of chemistry is built on quantum mechanics. Without it, we'd still be in the 19th century technologically. But here's the uncomfortable truth that physicists have been wrestling with for over 100 years. Despite quantum mechanics being so incredibly successful at predicting what will happen in experiments, we still don't really understand what it means. The mathematics tells us how to calculate probabilities, how to predict measurement outcomes, how to design quantum technologies. But it doesn't tell us what's actually happening. It doesn't explain what particles really are, why they behave the way they do, or what the universe looks like when nobody's watching. This gap between mathematical prediction and physical understanding is where the paradoxes live. They emerge whenever we try to interpret what the equations are telling us about reality. Whenever we ask questions like, what is really happening when we measure a particle? Or do particles have definite properties before we measure them? Or how can two particles be connected in a way that transcends space? The moment we move from calculating outcomes to understanding meaning, we run into contradictions, impossibilities, and scenarios that seem to violate our most basic intuitions about how reality should work. And here's what makes this situation truly extraordinary. These aren't fringe ideas or speculative theories. The giants of 20th century physics, the people who built quantum mechanics and proved its validity, were themselves deeply troubled by what they had created. Richard Feynman, one of the most brilliant physicists of his generation, famously said that nobody understands quantum mechanics, not because people aren't smart enough, but because the theory itself seems to resist understanding in any conventional sense. Niels Bohr, one of the founding fathers of quantum theory, declared that anyone who isn't shocked by quantum mechanics hasn't understood it. Roger Penrose, a Nobel Prize winner for his work on black holes, stated bluntly that quantum mechanics makes absolutely no sense. Perhaps most tellingly, Albert Einstein, whose work on the photoelectric effect helped launch quantum theory, spent the last decades of his life arguing that quantum mechanics must be incomplete. He couldn't accept that the universe operates on probability and uncertainty at its core. His famous quote, "God does not play dice with the universe," expressed his conviction that there must be a deeper, more deterministic theory underlying quantum mechanics. And Erwin Schrödinger, whose wave equation is the cornerstone of quantum mechanics, eventually said he regretted ever having anything to do with quantum theory, because the implications disturbed him so deeply. These weren't people who were afraid of new ideas or resistant to change. These were the most creative, revolutionary thinkers in the history of physics. They built the theory, proved it worked, and then spent years grappling with the philosophical implications of what they had discovered. And many of them died still uncertain about what it all meant. That uncertainty persists today. Modern physics has confirmed quantum mechanics to even greater precision. We've discovered new quantum effects, built quantum computers, and explored quantum behavior in increasingly complex systems. But the fundamental questions remain unanswered. What is a quantum measurement? What is the wave function really describing? Do unobserved particles have definite properties? How does quantum behavior give rise to the classical world we experience? These questions aren't just philosophical niceties, they cut to the heart of what science is supposed to do: explain reality. The paradoxes we're about to explore aren't mathematical errors or experimental flukes. They're real features of quantum mechanics that force us to question our most basic assumptions. They suggest that time might not flow in only one direction. That observation might not be passive but actively creative. That reality might not be singular but observer-dependent. That particles might not be localized objects but spread out patterns of possibility. That information might not be able to disappear, even in black holes. That consciousness itself might play a role in shaping physical reality. Some of these ideas sound like science fiction or mysticism, but they emerge directly from serious scientific experiments and rigorous mathematical analysis. They're not fringe theories promoted by outsiders. They're mainstream puzzles that appear in peer-reviewed journals and Nobel Prize acceptance speeches. They're the problems that define the cutting edge of theoretical physics, the frontier where our knowledge gives way to profound mystery. What makes quantum paradoxes so powerful is that they can't be dismissed or explained away easily. They're not the result of insufficient technology or incomplete data. They emerge from the logical structure of quantum theory itself. They're not problems we'll solve by building better detectors or running more careful experiments. They're problems that suggest quantum mechanics, for all its success, might be pointing towards something even deeper that we haven't grasped yet. This is why studying these paradoxes matters. They're not just curiosities for academics to debate in journals that nobody reads. They're clues. They're the universe telling us that we're missing something important. In the history of physics, every major revolution began with paradoxes that couldn't be resolved within the existing framework. The paradoxes of planetary motion led to Newton's laws. The paradoxes of light and electromagnetism led to relativity. The paradoxes of atomic spectra and black body radiation led to quantum mechanics itself. Each time, the paradoxes weren't obstacles to understanding. They were the pathway to a deeper, more complete theory. We might be at another one of those turning points now. The quantum paradoxes we'll explore might be telling us that we need a new framework entirely. Not one that replaces quantum mechanics, which works too well to be wrong, but one that explains why quantum mechanics takes the form it does. A theory that makes sense of superposition, entanglement, measurement, and all the other strange features that currently seem mysterious. Or perhaps the paradoxes are telling us something even more radical. That the universe doesn't work the way we've always assumed. That reality is fundamentally different from the picture that classical physics painted. That we need to abandon some of our deepest intuitions about time, space, causality, and existence itself. That the weirdness isn't a temporary confusion that will be cleared up eventually, but a permanent feature of reality that we need to learn to accept. Whatever the answer turns out to be, the journey begins with understanding the paradoxes themselves, with seeing exactly where and how our understanding breaks down, with confronting the strange experimental results and the uncomfortable implications head-on, without trying to soften them or explain them away prematurely. So let's begin that journey. Let's look at the quantum paradoxes that have puzzled physicists for decades and continue to puzzle them today. Let's see what they tell us about the nature of reality, time, observation, and existence. And let's see if we can glimpse even dimly what the universe might really be like beneath the quantum veil. One of the most mind-bending paradoxes in quantum mechanics involves something called the delayed choice quantum eraser. If you've heard about the famous double slit experiment, you might think you understand quantum weirdness. But the quantum eraser takes everything to another level entirely. It's not just strange, it seems to violate our most basic understanding of time and causality. And yet it's been performed successfully in laboratories around the world, with results that match the theoretical predictions perfectly. To understand what makes this experiment so disturbing, we need to start with the basics of quantum behavior. Imagine you're firing single photons, individual particles of light, toward a barrier with two possible paths they could take. Maybe these are two slits they could pass through, or two different routes through a system of mirrors and beam splitters. The key point is that each photon has a choice between path A and path B. Now, if you don't try to detect which path the photon takes, something remarkable happens. The photon doesn't go through one path or the other. It goes through both simultaneously. It exists in what's called a superposition, a combination of both possibilities at once. And because it takes both paths, it can interfere with itself, creating a characteristic interference pattern when many photons are detected. This interference pattern, with its alternating bright and dark bands, is the signature of wave-like behavior. It proves that the photon was acting like a wave spread across both paths, not like a particle taking one definite route. But here's where things get interesting. If you place a detector to measure which path the photon takes, the interference pattern disappears completely. Now the photon behaves like a classical particle, going through either path A or path B, but not both. The wave-like behavior vanishes the moment you gain information about which path was taken. It's as if the photon knows whether you're watching and changes its behavior accordingly. Not because the detector physically disturbs the photon, though that happens too, but because the mere existence of which path information seems to force the photon to choose a definite path. This is already extremely strange. The same photon behaves completely differently depending on whether path information is available, even if that information isn't actually looked at by a human. The detector doesn't need to display the result or record it anywhere accessible. The mere fact that the information exists in principle seems to be enough to change the photon's behavior from wave-like to particle-like. Now comes the truly disturbing part. The delayed choice quantum eraser asks what happens if you wait to decide whether to keep or erase the path information until after the photon has already completed its journey. You let the photon pass through the entire apparatus. You let it hit a detector screen and register its position. Only then, after the photon has finished traveling and its location has been recorded, do you make a choice about whether to preserve the which path information or erase it. The setup works like this. After the photon goes through the two paths, it hits the screen and its position is recorded. But the photon's journey doesn't end there. The experimental apparatus includes additional elements that can either preserve information about which path was taken or destroy that information. And crucially, this choice can be made after the photon has already hit the screen. You can decide after the fact whether path information will be available or not. What happens is shocking. If you choose to erase the path information after the photon has already been detected, and you sort the detection events based on this choice, you find that those photons show an interference pattern. If you choose to keep the path information, those photons show no interference pattern. The photon's behavior at the screen, which already happened in the past, seems to depend on a decision you make in the future. Let's be absolutely clear about what this means. The photon hit the screen at time t. Its position was recorded. That's a fact that's now in the past. But at time t plus 1 second, or 1 minute, or 1 hour, you make a decision about whether to erase path information. And when you analyze the data, sorting the photons based on your future decision, you find that the photons that will have their path information erased show wave-like behavior at the screen, while the photons that will have their path information preserved show particle-like behavior at the screen. Your future choice seems to affect the photon's past behavior. Now, it's absolutely critical to understand what this does and doesn't mean. The individual photons don't change position after they've been detected. The spots on the screen don't physically move. What changes is the pattern that emerges when you sort all the photons into groups based on what happened to their path information later. When you group together all the photons whose path information was erased, those photons form an interference pattern. When you group together all the photons whose path information was preserved, those photons show no interference pattern. This means you can't use this setup to send information backward in time. You can't look at the screen and know in advance whether the path information is going to be erased or not. The interference pattern only becomes visible when you do the sorting based on information that becomes available later. It's only in retrospect, only after both measurements have been completed, that you can see how the photon's earlier behavior correlated with the later choice. But even with these caveats, the delayed choice quantum eraser is profoundly disturbing. It suggests that the photon doesn't have a definite history until the entire sequence of measurements is complete. The photon exists in a kind of limbo, not fully committed to wave-like or particle-like behavior until the question of path information is finally settled, and that can happen after the photon has finished its journey. Some physicists try to explain this by arguing that the photon's wave function encompasses the entire experimental setup, including the future measurement. From this perspective, the photon isn't really in the past when it hits the screen. The entire experiment, from beginning to end, is one unified quantum system. The wave function describes all possible outcomes across all times, and it only resolves into a definite history once all measurements are complete. Others suggest that we need to rethink how time works in quantum mechanics. Maybe the classical picture of time, where events proceed in a fixed sequence from past to future, isn't quite right at the quantum level. Maybe quantum events don't have a definite temporal order until they're observed. Maybe the past is not a series of definite facts, but rather a probability distribution that gets refined as new information becomes available. Then there are interpretations that take the retrocausal possibility seriously. They suggest that quantum mechanics might genuinely allow future events to influence past ones, at least in a limited statistical sense. Not in a way that lets you change history or send messages to your past self, but in a way that means the full description of a quantum event requires information from both its past and its future. The event is determined by boundary conditions on both ends of its timeline. Each of these interpretations has its supporters and its problems. None of them fully resolves the paradox in a way that makes everyone comfortable. The delayed choice quantum eraser remains one of the clearest demonstrations that something very strange is going on with time, observation, and reality in quantum mechanics. Think about how alien this is to our everyday experience. Imagine playing basketball, shooting the ball toward the hoop, watching it go through the net, and then hours later deciding whether you had your eyes open or closed when you shot it, and somehow that decision changes whether the ball went through the net or bounced off the rim. That's the level of temporal weirdness we're dealing with here, except it's not a thought experiment. It's a real result that's been demonstrated in actual laboratories. The delayed choice quantum eraser tells us that the act of measurement isn't a simple one-time event. It's part of an extended process that can reach backward through time to determine what happened earlier. It tells us that which path information, the mere existence of data about which route a particle took, has a physical effect on the particle's behavior even before that data is created. It tells us that the distinction between wave-like and particle-like behavior isn't determined at the moment the photon encounters the two paths, but rather remains undecided until all measurement choices have been made. This has profound implications for how we think about reality. In classical physics, the past is fixed. What happened, happened. The present can be influenced by the past, but the past cannot be influenced by the future. That's the basis of causality, and it's one of the most fundamental principles in all of science. But the delayed choice quantum eraser suggests that in quantum mechanics, this principle might need to be modified. The past might not be fully determined until the future unfolds. Some people find this liberating, a suggestion that reality is more fluid and interconnected than we thought. Others find it deeply troubling, a hint that the orderly causal structure we rely on might be an illusion that breaks down at the quantum level. But regardless of how it makes you feel, the experimental results are clear. When you perform this experiment, you get these results. Every time. Without exception. The delayed choice quantum eraser is a perfect example of how quantum paradoxes work. It's not that we don't understand the mathematics. The theory makes a prediction, and the experiment confirms it precisely. The problem is that we don't know what the mathematics means. We don't know how to translate the equations into a story about what's actually happening in space and time. Every attempt to do so leads to something that violates our intuitions, whether it's retrocausality, timeless wave functions, or reality that doesn't exist until it's observed. And that's what makes it a paradox in the truest sense. Not a logical contradiction that proves the theory is wrong, but a situation where every possible interpretation seems impossible or deeply counterintuitive. It's the universe telling us that our concepts of time, causality, and reality need to be revised. We just haven't figured out yet how to revise them. While the delayed choice quantum eraser challenges our understanding of time, another paradox attacks something even more fundamental, the nature of reality itself. It's called Wigner's friend, and it asks a deceptively simple question. If two observers measure the same quantum system, do they necessarily agree on what happened? In classical physics, the answer is obviously yes. Reality is objective. If something occurs, everyone who observes it should see the same thing. But quantum mechanics suggests this might not always be true. The thought experiment was proposed by physicist Eugene Wigner in 1961. Here's how it works. Imagine a laboratory that's completely isolated from the outside world. Inside this lab is a quantum system, let's say a particle that's in a superposition of two states. We can call these states spin up and spin down, though the exact physical property doesn't matter much for the argument. The important point is that before measurement, the particle is in both states simultaneously according to quantum mechanics. Now imagine there's a scientist inside this laboratory. Let's call this person Wigner's friend. The friend performs a measurement on the quantum system and obtains a definite result. Let's say the measurement shows spin up. From the friend's perspective, the measurement has collapsed the superposition. The particle is no longer in both states. It has been determined to be spin up. The quantum indeterminacy has been resolved. Reality has settled into a definite state. So far, this is just standard quantum mechanics. The friend made a measurement, got a result, and the system collapsed from superposition into a definite state. Nothing controversial yet. But now add another layer. Wigner himself is outside the laboratory. He hasn't observed the measurement result. He hasn't interacted with the lab at all. From his perspective, what's the state of the quantum system? Here's where things get strange. According to quantum mechanics, if Wigner hasn't observed the system, then from his perspective, it's still in superposition. But here's the crucial point. The system now includes not just the particle, but also Wigner's friend. The friend interacted with the particle and became entangled with it. So from Wigner's external perspective, both the particle and the friend are in a superposition. The friend exists simultaneously in a state where they measured spin up and a state where they measured spin down. This creates a bizarre situation. From the friend's point of view, a definite measurement occurred. They saw spin up. That's their reality. There's no ambiguity from their perspective. But from Wigner's point of view, the measurement hasn't happened yet. The friend is in a superposition of having seen both results. Both perspectives are correct according to quantum mechanics, but they disagree fundamentally about what has occurred. Now, you might think this is just a matter of information. Maybe Wigner simply doesn't know what the friend observed, but there's still an objective fact about what happened. But quantum mechanics doesn't quite allow that interpretation. The mathematics says that if Wigner hasn't observed the system, then it truly is in superposition from his perspective. It's not that he doesn't know which state it's in, it's that both states genuinely exist in his version of reality until he makes his own observation. For many years, Wigner's friend was just a thought experiment that people argued about philosophically. You could debate what it meant without having to worry about testing it experimentally, because we can't actually put conscious observers into quantum superposition. But in recent years, physicists have found clever ways to test simplified versions of the scenario using quantum systems that can stand in for conscious observers. In 2019, researchers published a striking paper in Nature Communications where they created an experiment with multiple observers represented by quantum systems measuring entangled particles. They designed the setup so that two different observers could make measurements on the same system and, under certain conditions, record incompatible results. Not because someone made a mistake or because the measurements were imprecise, but because quantum mechanics allows different observers to experience genuinely different outcomes for the same event. These results aren't opinions or interpretations, they're actual physical measurements. Observer A performs a measurement and records one outcome. Observer B performs a measurement and records a different outcome, and both are correct within their own frame of reference. This suggests that reality might actually be observer-dependent in quantum mechanics, not just our knowledge of reality, but reality itself. Let's think about what this means. In classical physics, there's one universe with one set of facts. If two people disagree about what happened, at least one of them is wrong or misinformed or lying. But Wigner's friend suggests that in quantum mechanics, two observers can both be right while disagreeing about what happened. They're not experiencing the same reality differently, they're experiencing different realities. The many worlds interpretation of quantum mechanics offers one way to make sense of this. According to many worlds, every quantum measurement causes the universe to branch into multiple versions, with each possible outcome occurring in a different branch. In this view, Wigner's friend measures the particle and splits into two versions, one who saw spin up and one who saw spin down. From Wigner's external perspective, he's still in a superposition that includes both of these branches. When he finally makes his own measurement, he splits two, entering one branch or the other. Both observers are correct, but they're in different branches of reality, and they never quite share the same complete view of what happened. Other interpretations handle the paradox differently. The Copenhagen interpretation, which dominated thinking about quantum mechanics for decades, simply sidesteps the issue by saying that measurement causes collapse and treating the observer as somehow outside the quantum system. But this leaves vague exactly what counts as an observer and why observers are special. If Wigner's friend is an observer who can collapse wave functions, then the measurement is real from their perspective. But if only Wigner is a true observer, then the friend might still be in superposition. Relational quantum mechanics takes yet another approach. It argues that quantum states are always relative to an observer. There's no absolute description of the quantum system. Instead, the friend has one description relative to themselves, where the measurement definitely happened, and Wigner has a different description relative to himself, where the measurement hasn't happened yet. Both descriptions are valid, and there's no deeper objective reality beneath them. This interpretation says that reality itself is fundamentally relational, always described from a particular perspective, never from a God's eye view. Each of these interpretations tries to resolve Wigner's friend, but none of them does so in a way that everyone finds satisfying. Many worlds avoids the contradiction by multiplying realities. Copenhagen avoids it by making observers special in an undefined way. Relational quantum mechanics avoids it by denying objective reality altogether. Every solution comes with a cost, and that cost is giving up something we thought was fundamental about how the universe works. What makes Wigner's friend particularly disturbing is that it forces us to confront the possibility that reality might not be singular. We're so accustomed to thinking there's one world, one set of facts, one truth about what happened. Even when people disagree about events, we assume there's an objective reality that would settle the dispute if we had perfect information. But Wigner's friend suggests that perfect information might not exist. Different observers with complete information might still disagree, not because they're wrong, but because they're each correct within their own reference frame. Think about the implications of that. It would mean that when two people have a conversation, they're not necessarily talking about the same reality. Their experiences, their observations, their measurements might all correspond to slightly different versions of the universe. In everyday life, these differences would be so tiny as to be completely unnoticeable. Classical physics emerges as a good approximation when quantum effects average out. But in principle, at the most fundamental level, each observer might inhabit their own branch of reality, their own version of what's real. This connects to other mysteries in quantum mechanics too. It relates to the measurement problem, the question of what causes wave function collapse. If different observers can witness different collapses, or if collapse is relative to the observer, then collapse isn't a singular objective event. It's something more subtle and observer-dependent. This also connects to the question of consciousness in quantum mechanics. If making an observation affects what becomes real, and different observers can observe different things, then maybe consciousness isn't just passively receiving information about a pre-existing reality. Maybe it's actively participating in creating that reality, or at least in defining which version of reality you experience. Wigner himself eventually came to believe that consciousness plays a special role in quantum mechanics, that it's consciousness that causes wave function collapse. Many physicists are uncomfortable with this idea because it seems to mix physics with philosophy or even mysticism. But Wigner's friend makes it hard to avoid the question. If the friend is conscious and experiences a definite result, while Wigner sees the friend in superposition, then consciousness seems to create a boundary where quantum superposition ends and classical definiteness begins. And that boundary appears to be different for different observers. The experimental confirmations of observer-dependent reality in quantum systems make this more than philosophical speculation. We can actually create situations where different parts of an experiment record different realities. We can show that quantum mechanics doesn't always resolve into one coherent story that everyone agrees on. This is not a failure of quantum mechanics. The theory predicts exactly these results. It's a feature, not a bug. But it's a deeply strange feature that challenges everything we thought we knew about objectivity and truth. Wigner's friend isn't asking whether quantum mechanics is correct. It's asking what quantum mechanics means. And the answer it suggests is unsettling. Reality might not be the solid, objective, singular thing we've always assumed. It might be more like a kaleidoscope, where different observers see different patterns, all equally valid, all emerging from the same underlying quantum state, but none of them representing the complete objective truth because such a thing might not exist. This paradox is still debated actively today. As quantum technologies advance, as we build better quantum computers and communication systems, the question of observer-dependent reality becomes more than academic. If we're building machines that operate on quantum principles, we need to understand what reality looks like from those machines' perspectives. And Wigner's friend tells us it might not be the same reality we experience. The paradox remains unresolved. Different physicists favour different interpretations, and no interpretation has won unanimous acceptance. What everyone agrees on is that Wigner's friend reveals something profound about the nature of observation, measurement, and reality in quantum mechanics. It shows that these concepts are far more mysterious than they appear, and it reminds us that even after a century of quantum mechanics, we still don't fully understand what the theory is telling us about the world. If the previous paradoxes weren't strange enough, let's push things even further. Let's talk about time itself and whether the future might actually influence the past. This idea, called retrocausality, sounds like science fiction. In our everyday experience, time flows in one direction. Causes precede effects. What happens now can influence what happens later, but what happens later cannot reach back and change what happened before. That's causality, and it's one of the most fundamental principles we have. But quantum mechanics suggests this picture might be too simple. The equations that describe quantum systems don't inherently prefer one direction of time over another. They're time symmetric, meaning they work equally well whether time runs forward or backward. This mathematical property hints that maybe time isn't quite what we think it is, at least not at the quantum level. The most direct evidence for something strange happening with time comes from experiments like the delayed choice quantum eraser we discussed earlier. Remember, in that setup, a decision made after a photon completes its journey seems to affect how the photon behaved earlier in its path. The mathematics works out perfectly, the experiments confirm the predictions, but the explanation, the story we tell about what's actually happening, inevitably involves something that feels like backward causation. Retrocausality takes this observation seriously. Instead of treating backward time effects as just an illusion or an artifact of how we analyze the data, retrocausality proposes that quantum events might genuinely be influenced by both their past and their future. Not in a way that lets you change history or create grandfather paradoxes, but in a subtle way where the complete description of a quantum event requires information from both ends of its timeline. One of the most developed approaches to retrocausality is something called the two-state vector formalism. In standard quantum mechanics, you describe a system with a wave function that evolves forward in time from some initial state. This wave function tells you the probabilities for different measurement outcomes. The two-state vector formalism adds a second wave function that evolves backward in time from a final state. The system is described by both of these wave functions simultaneously, one coming from the past and one coming from the future. The actual behavior you observe is determined by how these two wave functions interact. Think of it like this. Imagine you're describing the path of a river. You could describe it by starting at the source in the mountains and following the water as it flows downhill toward the ocean. That's the normal forward time description. But you could also describe it by starting at the ocean and working backward, tracing the river upstream to its source. In classical physics, these two descriptions would give you the same river. But in the two-state vector formalism, both descriptions are needed to fully capture what's happening. The river's flow at any point is determined by both where it came from and where it's going. This approach has some appealing features. For one thing, it doesn't require wave function collapse. In standard quantum mechanics, we have this awkward moment where the wave function suddenly collapses when a measurement is made, jumping from a superposition of possibilities to a single definite outcome. But in the two-state vector formalism, there's no sudden collapse. Instead, the forward-evolving and backward-evolving wave functions combine smoothly to determine what you observe. The apparent collapse is just the result of having boundary conditions at both the beginning and end of the process. It also makes certain quantum phenomena easier to understand. For example, the delayed choice quantum eraser becomes less paradoxical if you allow future boundary conditions to influence past behavior. The photon's behavior at an earlier time is partially determined by what happens to it later, so there's no mystery about why a later choice affects earlier statistics. It's built into how the quantum state is defined. But retrocausality also raises profound questions about free will and determinism. If future events can influence past ones, then maybe the future is already fixed in some sense. Maybe your choices aren't as free as you think because they're part of a larger pattern that includes both what came before and what comes after. This leads toward what philosophers call the block universe view, where all of time exists simultaneously as a single four-dimensional structure. Past, present, and future are all equally real, just different regions of this block. You don't move through time, you're spread across it, like a static sculpture extending through the fourth dimension. Some people find this view comforting. It suggests a kind of order and permanence to existence. Everything that will ever happen has, in some sense, already happened from a timeless perspective. Others find it deeply unsettling because it seems to eliminate any real sense of freedom or agency. If the future is already part of the structure of space-time, then your choices are just playing out a predetermined pattern, even if you experience them as free in the moment. Retrocausality doesn't necessarily require the block universe, but they fit together naturally. If time is really just another dimension like space, if past and future are just directions rather than fundamentally different kinds of things, then there's no reason why influences should only flow one way. In a block universe, causation might run in both temporal directions. It's important to emphasize what retrocausality doesn't mean. It doesn't mean you can send information to your past self. It doesn't mean you can change what already happened. Those kinds of time travel scenarios create logical paradoxes like the grandfather paradox, where you go back and prevent your own birth. No version of retrocausality in quantum mechanics allows for that kind of thing. Information can't propagate backward through time in a way that would let you send messages or alter the past in a controllable fashion. What retrocausality does suggest is something more subtle. The complete causal story of an event might require looking both backward to its causes and forward to its effects. The event is constrained by boundary conditions on both ends. It's like solving a maze where you know both the starting point and the ending point. You can work backward from the end just as easily as you can work forward from the beginning, and the actual path through the maze is determined by both constraints simultaneously. This has interesting implications for quantum entanglement, that spooky connection between particles that Einstein found so troubling. When two particles are entangled, measuring one instantly seems to affect the other, no matter how far apart they are. This appears to involve faster-than-light influence, which would violate relativity. But if you allow retrocausality, you can explain entanglement without any faster-than-light signaling. The correlation between the two measurements could be explained by both measurements being constrained by future boundary conditions, not by one measurement causing the other through some mysterious instantaneous connection. Some physicists like this approach because it preserves locality, the idea that objects can only be directly influenced by their immediate surroundings. In a retrocausal picture, when you measure an entangled particle here, you're not sending a signal to its partner over there. Instead, both measurements are consistent with each other because they're both constrained by the same future boundary condition. The universe is self-consistent across time, and that self-consistency creates the correlations we observe. Other physicists are skeptical. They argue that retrocausality just pushes the mystery somewhere else without really solving it. Instead of asking how can two particles coordinate without a signal between them, you're asking how can future events constrain past ones. You've traded one counterintuitive idea for another. And there's the question of whether retrocausality is even testable. If it doesn't allow you to send information backward, If its effects are always statistical and only visible in retrospect, can we ever really prove it's happening? There have been some proposals for experiments that might distinguish retrocausal models from other interpretations of quantum mechanics. These typically involve very careful analysis of timing and correlations in quantum systems. But so far, no experiment has definitively proven that retrocausality is real, rather than just a useful way to think about the mathematics. It remains an open question in quantum foundations. What makes retrocausality worth taking seriously is that it emerges naturally from the mathematical structure of quantum mechanics. The equations don't have a built-in arrow of time. They're symmetric, and when you try to interpret what those symmetric equations mean in terms of physical processes, retrocausality is one of the options that shows up. It's not something people invented because they wanted time to work backward. It's something the mathematics suggests when you take it seriously. This connects to a broader question about the nature of time itself. In classical physics, and in our everyday experience, time seems fundamentally different from space. You can move freely in any direction through space, but you're carried inexorably forward through time. The past is fixed and unchangeable. The future is open and undetermined. This asymmetry between past and future, sometimes called the arrow of time, seems absolutely fundamental to how we experience reality. But where does this arrow come from? The fundamental laws of physics, both classical and quantum, are almost entirely time-symmetric. If you filmed a collision between two billiard balls and played the video backward, the reversed motion would still obey Newton's laws perfectly. The same is true for quantum mechanics. The Schrödinger equation works just as well backward as forward. So why does time seem to have a direction? The usual answer involves entropy and the second law of thermodynamics. Entropy, roughly speaking, measures disorder or randomness. The second law says that entropy tends to increase over time in closed systems. This gives time a direction. The past is the direction of lower entropy. The future is the direction of higher entropy. A broken egg has higher entropy than an intact egg, and you never see entropy spontaneously decrease, never see a broken egg reassemble itself. That's why time seems to flow forward. But entropy is a statistical concept. It emerges from the behavior of large numbers of particles. At the level of individual particles and quantum systems, there's no entropy increase built into the fundamental laws. So the arrow of time might not be a fundamental feature of reality. It might be something that emerges only when you have complex systems with many degrees of freedom. At the quantum level, where you're dealing with individual particles or small numbers of particles, maybe time doesn't have a preferred direction at all. If that's true, then retrocausality becomes less strange. It's not that effects are reaching backward through time in some magical way. It's that our intuition about time flowing forward is based on macroscopic experience and doesn't necessarily apply at the quantum scale. At the deepest level of reality, time might be more like space, just another dimension that can be traversed in either direction, with the apparent asymmetry being something that emerges only at larger scales. This is speculative, and many physicists would disagree. But it's the kind of speculation that quantum mechanics encourages. The theory keeps showing us that our intuitions, formed by everyday experience in a classical world, don't necessarily apply when we look at the quantum foundation. Time might be one more intuition that needs to be revised. The debate over retrocausality continues. Some researchers are actively developing retrocausal models of quantum mechanics, trying to show they can explain quantum phenomena more naturally than standard approaches. Others remain skeptical, preferring interpretations that preserve the familiar forward flow of causation. And still others think the whole question is misguided, that we're trying to impose classical notions of causality onto a quantum world that doesn't work that way at all. What everyone can agree on is that time in quantum mechanics is strange. The delayed choice quantum eraser proves that experimentally. How we interpret that strangeness, whether as retrocausality or timeless wave functions or something else entirely, remains an open question. But the experiments themselves are undeniable. The future does something in quantum mechanics that affects how we understand the past, even if we don't yet fully understand what that something is. Moving from the mysteries of time to the puzzles of space, we encounter another deeply strange quantum phenomenon. It's called quantum entanglement, and when applied to certain games and experiments, it produces an effect so bizarre it's been nicknamed quantum pseudo-telepathy. This isn't actual telepathy, no minds are being read, but the results look so much like it that the name is hard to avoid. To understand what's happening, imagine a simple game. You and a friend are separated and placed in different rooms where you can't communicate. Each of you will be asked a question chosen randomly from a list, and you must answer yes or no. The questions and answers are designed so that if your responses match in specific ways, you both win. If they don't match correctly, you lose. In the classical world, the best you could do is agree on a strategy beforehand. You could memorize a chart, plan your responses for every possible combination of questions, and hope for the best. But no matter how clever your strategy, there will always be some combinations of questions where classical physics guarantees you can't both give the right answer. The mathematics of probability puts an absolute limit on your success rate. You might win 80% of the time with a perfect classical strategy, but you'll never win every time. Now imagine that before you're separated, you and your friend each take one particle from a pair of entangled quantum particles. These particles have a very strange property. They're described by a single quantum state, a single wave function that encompasses both of them together. They're not two separate objects that happen to be correlated. They're part of one quantum system that's been spatially separated. When the game begins and you receive your question, you measure your particle in a particular way, chosen based on the question. Your friend does the same with their particle based on their question. Neither of you knows what the other measured or what result they got. You're still completely isolated. No information passes between you during the game. But when your answers are compared afterward, something remarkable happens. They match in a way that would be impossible with any classical strategy. Your success rate exceeds the theoretical maximum for classical methods. This has been demonstrated in real laboratories. It's not speculation or thought experiment. Quantum entanglement allows players to coordinate their responses in ways that classical physics absolutely forbids. The effect is so striking that it feels like the players are reading each other's minds or communicating through some hidden channel. But they're not. There's no signal passing between them. No information is transferred. The particles were entangled at the beginning, and that entanglement is enough to produce the correlations. One of the most famous examples is called the magic square game. It involves a 3x3 grid that players must fill with ones and negative ones. The rules specify that certain rows must multiply to 1 and certain columns must multiply to -1. Due to the mathematical constraints, it's impossible to fill the grid correctly using any classical method. There's always at least one contradiction. But if the players use entangled quantum particles to generate their numbers, they can win every single time. The quantum strategy achieves what classical logic says is impossible. Another example is the GHZ game, named after physicists Greenberger, Horn, and Zeilinger. In this game, 3 players are involved. They each receive a question and must provide an answer, and the answers must satisfy certain parity constraints. Again, classical physics puts a limit on how often they can succeed. But with quantum entanglement shared among all 3 players, they can achieve perfect coordination. The correlations between their answers are stronger than anything classical probability allows. What's really going on here? At the heart of it is the nature of quantum entanglement. When two particles are entangled, they don't have independent properties. They're not like two coins that are already heads or tails before you look. Instead, their properties are fundamentally connected. Measuring one particle doesn't reveal a pre-existing property. It actualizes a property that wasn't definite before. And due to the entanglement, when you actualize a property in one particle, you're automatically affecting what properties the other particle can have. But here's the crucial point. Even though the two particles are connected, no information travels between them. This was proven definitively by John Bell in the 1960s and confirmed by countless experiments since then. The particles are correlated, but the correlation can't be used to send a signal. If you just look at one particle's measurements in isolation, they appear completely random. It's only when you bring both sets of measurements together and compare them that the correlations become visible. This is why it's pseudo-telepathy rather than actual telepathy. Real telepathy would let you learn something about a distant location instantly. But quantum entanglement doesn't do that. You can't use it to send messages. You can't look at your measurements and know what your partner measured. The information only appears when you combine data from both locations, which requires normal, slower than light communication. Nevertheless, the correlations are real and they're strong enough to win games that are unwinnable classically. This tells us something profound about the nature of reality. It suggests that the world isn't made of separate, independent objects that occasionally interact. At the quantum level, things can be connected in ways that transcend space. The entangled particles are one system, not two, and that oneness persists even when the particles are separated by vast distances. Einstein famously called this spooky action at a distance, and he hated it. He thought it meant quantum mechanics was incomplete, that there must be hidden variables, additional information we're not accounting for that would explain the correlations in a more reasonable way. In 1935, together with Boris Podolsky and Nathan Rosen, Einstein wrote a paper arguing that quantum mechanics couldn't be the whole story. Their thought experiment, now called the EPR paradox, was meant to show that either quantum mechanics was incomplete or it violated locality, the principle that objects can only be influenced by their immediate surroundings. Einstein was sure that locality had to be preserved, so he concluded quantum mechanics must be incomplete. But decades later, John Bell proved mathematically that no theory based on local hidden variables could reproduce all the predictions of quantum mechanics. And then experiments confirmed that quantum mechanics was right and Einstein's intuition was wrong. The correlations in entangled systems really do exceed what any local realistic theory can explain. This leaves us with some uncomfortable choices. We can give up locality and accept that entangled particles are genuinely connected in a non-local way that doesn't respect spatial separation. Or we can give up realism, the idea that particles have definite properties, independent of measurement. Or we can accept both quantum mechanics and locality, but give up counterfactual definiteness, the assumption that unperformed measurements would have yielded definite results if they had been performed. Each option challenges some fundamental assumption about reality, and quantum pseudo-telepathy demonstrates this challenge in a very direct way. It shows that the world contains correlations that shouldn't be possible if reality were local and realistic in the classical sense. The players in these quantum games are coordinating in a way that transcends normal cause and effect, not because they're cheating or because there's a hidden signal, but because quantum entanglement creates a form of connection that classical physics never imagined. Some interpretations of quantum mechanics handle this better than others. In the many worlds interpretation, The entangled particles are part of one large quantum system that includes both measurement devices and both observers. When measurements are made, the whole system branches, with different outcomes occurring in different branches. The correlations appear perfect within each branch because the branches are self-consistent. There's no non-local signal needed because everything is part of one unified quantum state that evolves deterministically. In Bohmian mechanics, another interpretation, particles do have definite positions at all times, but they're guided by a pilot wave that is genuinely non-local. The pilot wave connects entangled particles instantly across space, creating the correlations we observe. This preserves realism, but gives up locality explicitly. In relational quantum mechanics, the correlations are explained by saying that quantum states are always relative to an observer. The two players don't share an objective quantum state. Each has their own description relative to their own measurements, but these descriptions are constrained to be mutually consistent, which produces the correlations. Each interpretation offers a different story about what quantum pseudo-telepathy means. But the experimental facts don't change. Entanglement produces correlations that exceed classical limits. It allows coordination without communication. It demonstrates that the quantum world is fundamentally non-classical in ways that directly affect how systems can interact and correlate. This has practical implications too. Quantum cryptography uses entanglement to create communication channels that are provably secure. Any eavesdropper trying to intercept the quantum signals would disturb the entanglement and be detected. Quantum computing uses entanglement to perform certain calculations that would be impossible on classical computers. The correlations between entangled quantum bits allow quantum computers to explore many possibilities simultaneously in a way that classical bits cannot. But beyond the applications, quantum pseudo-telepathy is philosophically profound. It demonstrates that the universe contains connections that transcend space in the way we normally understand it. Two particles, two systems, two observers can be correlated in ways that seem to require faster than light communication, but actually don't involve any communication at all. They're connected at a level deeper than spatial separation, connected through the quantum state that describes them as a unified whole. This challenges our basic intuition that the universe is made of separate things that occasionally bump into each other. At the quantum level, separation might be an illusion. What looks like two distinct objects might actually be two aspects of one quantum system. Space separates them in one sense, but not in the deeper quantum mechanical sense. They remain entangled, remain part of one wave function, remain capable of producing correlations that transcend distance. Quantum pseudo-telepathy shows us that the universe is weirder than we thought, not in a vague, hand-waving way, but in a precise, experimentally verified, mathematically rigorous way. The games that can be won with quantum entanglement, but not with classical strategies, prove that reality operates by rules that don't fit our classical intuitions. And every time we test these rules, they hold up. The universe really does allow this kind of non-local coordination. We just don't fully understand yet what that means about the nature of space, separation, and connection. If quantum mechanics can separate what shouldn't be separable, if future events can influence past ones, if different observers can experience different realities, then perhaps it shouldn't surprise us that in the quantum world you can separate a thing from its properties. That's exactly what happens in one of the strangest quantum experiments ever performed, the Quantum Cheshire Cat. The name comes from Alice in Wonderland, where the Cheshire Cat famously disappears, leaving only its grin behind. In the quantum version, physicists have managed to do something conceptually similar. They've separated a particle from one of its fundamental properties, making the particle go one way while its property goes another. It sounds impossible, and in classical physics it would be. But in quantum mechanics, it's real. The experiment typically uses neutrons, subatomic particles that have both a position and a property called spin. Spin is a quantum mechanical property that doesn't have a perfect classical analogue. It's not literally the particle spinning like a top, but it behaves similarly in some ways. Every neutron has spin, and you can measure that spin along different directions. The spin is just as much a part of the neutron as its mass or charge. Or at least that's what we thought. The experimental setup uses an interferometer, a device that splits a particle's path into two routes. When a quantum particle enters an interferometer, it goes into a superposition of taking both paths simultaneously. This is standard quantum behavior. The particle isn't on path A or path B. It's on both until a measurement forces it to choose. But here's where things get clever. The researchers use a technique called weak measurement, which is a way of gathering information about a quantum system without completely collapsing its superposition. Instead of doing a strong measurement that forces the particle into a definite state, a weak measurement gently nudges the system and collects statistical information without, fully disturbing it. If you do many weak measurements on many identically prepared systems, you can piece together information about what's happening without destroying the quantum superposition in any individual case. Using weak measurements, the physicists can ask questions like, where is the neutron and where is the neutron's spin? And remarkably, the answers they get suggest that the neutron travels along one path while its spin travels along the other path. The particle and its property have been separated. Let's be very clear about what this means and what it doesn't mean. The neutron doesn't literally split into two pieces. You don't end up with a neutron here and a disembodied spin over there. What happens is more subtle. The weak measurement results indicate that if you were to look for the neutron, you'd most likely find it on path A, but if you were to look for its spin, you'd most likely find evidence of it on path B. The particle exhibits behavior consistent with its position being in one place and its spin being somewhere else. This is deeply weird because in classical physics, properties belong to objects. The spin is a property of the neutron. They're not separate things. The neutron has spin the way a ball has color, or a car has weight. You can't send the ball one direction and its color another direction. The color is a property of the ball, not an independent entity that can wander off. But quantum mechanics allows this separation, or rather, quantum mechanics doesn't forbid it, and when you do the experiment carefully, you find results that suggest it's happening. The Quantum Cheshire Cat shows that quantum systems don't behave like classical objects with a fixed set of properties glued to them. Instead, properties can be delocalized, spread out, or separated in ways that make no sense classically. One way to think about this is that quantum objects aren't really objects in the classical sense at all. They're more like clouds of probability, patterns of potential, structures of information that only take on definite form when measured. A neutron isn't a little ball with properties attached to it. It's a quantum state that has different aspects: position, spin, energy, momentum, and these aspects don't necessarily have to be localized together. They can spread out through space and even apparently separate under the right conditions. The weak measurement technique is crucial to observing this. If you did a strong measurement, checking definitively where the neutron is, you'd collapse the superposition and destroy the subtle effect you're trying to observe. The neutron would be forced into one path or the other, and its spin would come along with it. But weak measurements allow you to probe the system gently enough that the superposition persists and the strange separation remains visible. Critics of the Quantum Cheshire Cat interpretation argue that weak measurements can be misleading. The weak measurement results don't necessarily tell you where the particle or its spin really are. They tell you something about the quantum state, but interpreting that information in terms of separated properties might be reading too much into the data. The mathematics is unambiguous, but what it means physically remains debatable. Supporters counter that the weak measurement results are just as valid as strong measurement results. They provide information about the quantum system, and that information is telling us something real about how the system behaves. If the mathematics says the position and spin can be separated, then we should take that seriously rather than dismissing it because it doesn't fit our classical intuitions. This debate reflects a larger issue in quantum mechanics. The theory gives us powerful mathematical tools for predicting experimental outcomes, but it doesn't come with a clear interpretation of what the mathematics means. Different physicists read the same equations and come to different conclusions about what's really happening. The Quantum Cheshire Cat is a perfect example of this ambiguity. Everyone agrees on the experimental results and the mathematical description. The disagreement is about what story to tell, whether to say the particle and its spin actually separate, or to say the quantum state just behaves in a way that looks like separation when probed with weak measurements. Regardless of how you interpret it, the Quantum Cheshire Cat experiment reveals something important. Quantum systems are not classical objects. Their properties don't behave like classical properties. The intuitive picture we have of particles as tiny localized things with fixed characteristics is not accurate at the quantum level. Particles are more fluid, more context-dependent, more strange than that simple picture suggests. This connects to other quantum paradoxes too. It relates to the measurement problem because it shows that quantum properties don't exist in a definite way until they're measured. It relates to Wigner's friend because it suggests that what properties a system has might depend on how and when you look at it. It relates to entanglement because it demonstrates that quantum systems can have internal structures that don't respect classical notions of locality and separation. The Quantum Cheshire Cat also has implications for quantum information theory. If properties can be separated from particles, then maybe information can be separated and recombined in novel ways. This could lead to new quantum communication protocols or quantum computing techniques that exploit this kind of property separation. Some researchers have even proposed using the Quantum Cheshire Cat effect for quantum cryptography. If you could send a particle one way and it spin another way, you might be able to create communication channels that are even more secure than standard quantum cryptography, because an eavesdropper would have to intercept both the particle and its separated property to gain full information. Whether these applications will work out remains to be seen. The Quantum Cheshire Cat is still a relatively new experimental result, and physicists are still figuring out what it means and what can be done with it. But it's another example of how quantum mechanics continually surprises us, revealing new aspects of reality that don't fit our preconceptions. The image of a grin floating without a cat is memorable and disturbing. It captures something essential about quantum mechanics, the way the theory allows things that should be impossible, that violate basic assumptions about how reality works. A particle is supposed to have properties. Those properties are supposed to be where the particle is. Separating them shouldn't be possible. But quantum mechanics doesn't care about should. It cares about what the mathematics allows and what experiments reveal. And both the mathematics and the experiments say that in the quantum world, you really can have a grin without a cat, a property without the particle it belongs to, at least in some sense. This is unsettling, not just because it's strange, but because it challenges the very concept of what an object is. If a particle's properties can drift away from the particle itself, then what is the particle? Is it just a collection of properties that happen to be nearby most of the time, but can separate under special conditions? Is there a core particle that has properties, or are there just properties loosely associated with each other? Quantum mechanics doesn't provide clear answers to these questions. It just shows us that particles behave in ways that don't fit our classical categories. The Quantum Cheshire Cat remains an active area of research. Physicists continue to perform variations of the experiment, testing different systems and different measurement schemes, trying to understand exactly what's happening and what it tells us about quantum reality. As with so many quantum paradoxes, the mathematics is clear. The experiments are reproducible, but the meaning remains elusive. We can describe what happens, we can predict it accurately, but we still struggle to say what it really means about the nature of particles and properties and reality itself. Now let's turn to perhaps the most disturbing quantum thought experiment of all. The previous paradoxes were strange, challenging our understanding of time, observation, space, and properties. But this next one is personal. It asks what quantum mechanics might mean for consciousness, survival, and the very nature of subjective experience. It's called quantum suicide, or sometimes quantum immortality, and it takes the many worlds interpretation of quantum mechanics to its most extreme and uncomfortable conclusion. The thought experiment begins with the many worlds interpretation, which says that every time a quantum measurement occurs, the universe splits into multiple branches. Each possible outcome happens, but in a different branch. From our perspective, we experience only one outcome, but that's just because we're in one branch. All the other outcomes occur in other branches where other versions of us experience different results. Most discussions of many worlds focus on simple quantum events, a particle measured to be spin up in one branch and spin down in another. Your version of the universe sees one result, another version sees the other, and both branches are equally real. This is strange enough, but it gets much more disturbing when you apply it to matters of life and death. Imagine a device connected to a quantum random number generator. This device produces a truly random outcome based on quantum mechanics. Let's say a 50% chance of one result and 50% of the other. Now connect this device to something lethal. If the quantum result is 0, nothing happens. If it's 1, the device kills you instantly and painlessly. You sit in front of this device and activate it. In the many worlds interpretation, the universe splits. In half the branches, the result is 0 and you survive. In the other half, the result is 1 and you die. From an outside perspective, an observer watching you, there's a 50% chance you survive and a 50% chance you die. Nothing special about that. It's just a very grim coin flip. But now consider your subjective experience. In the branches where you die, your consciousness ends. You experience nothing after that point, but in the branches where you survive, your consciousness continues. And here's the key insight. Your stream of conscious experience can only continue in the branches where you survive. You never experience death because there's no you left to experience it in the branches where it occurs. Now suppose you activate the device again. Again the universe splits. In half the branches where you previously survived, you now die. In the other half, you continue living. From outside, the probability of survival after 2 trials is only 25%. But from your subjective perspective, you find yourself in the branch where you survived both times, because that's the only branch where your consciousness persists. Repeat this over and over. Each time the universe splits, and in most branches you die. But there's always at least one branch where you survive. From outside it looks increasingly unlikely. After 10 trials, only about 1 in 1,000 versions of you survive. After 20 trials, only 1 in 1,000,000. But from your first-person perspective, you keep finding yourself in the surviving branch because that's the only place your experience can continue. This leads to the unsettling concept of quantum immortality. According to many worlds, there will always be some branch of the universe where you survive any quantum chance event. It might be an incredibly improbable branch, but it exists. And your subjective experience necessarily continues through that branch because you can't experience the branches where you don't exist. This doesn't mean you're literally immortal in any practical sense. From everyone else's perspective, you probably died after a few trials. From the perspective of the universe as a whole, most versions of you died. But from your own internal first-person viewpoint, you never experience death. You always find yourself in the branch where you survived, no matter how improbable that branch becomes. Now extend this reasoning to more realistic scenarios. Every moment of your life presumably involves countless quantum events in your body and brain. Most of these events don't determine life or death, but some might. A random quantum fluctuation could trigger a fatal heart arrhythmia or prevent one. A quantum uncertainty in molecular bonds could lead to a dangerous mutation or not. If many worlds is correct, then in some branches these quantum events go one way and you die, while in other branches they go differently and you survive. Following the logic of quantum immortality, your consciousness always continues through whatever branches keep you alive. You might experience increasingly unlikely scenarios, narrow escapes, inexplicable survival of situations that should have killed you, but you keep surviving because the only branches you can experience are the ones where you continue to exist. This sounds appealing at first. Who wouldn't want to live forever, at least from their own perspective? But think about the implications more carefully. Quantum immortality doesn't guarantee that you survive healthily or comfortably. It only guarantees that you survive. The branches you continue through might be very unpleasant ones. You might be the sole survivor of disasters that kill everyone around you. You might be terribly injured but not quite dead. The branches where you persist might be increasingly improbable, increasingly strange, increasingly isolating. Moreover, quantum immortality says nothing about aging. You still get older. Your body still deteriorates. Eventually, you might find yourself in branches where you're extremely old, perhaps barely conscious, unable to die because your stream of consciousness keeps finding the improbable quantum events that sustain basic biological function. That's not immortality as anyone would want it. It's a horror scenario. And there's the question of whether this reasoning even makes sense. Quantum immortality depends entirely on the many worlds interpretation being correct, and on consciousness being the kind of thing that can meaningfully be said to continue through one branch but not others. But we don't really understand consciousness. We don't know if it's something that fundamentally splits along with quantum branches, or if the whole concept of subjective continuity through branching universes is coherent. Most physicists, even those who favour many worlds, are skeptical of quantum immortality. They point out that even if many worlds is correct, the vast majority of your measure, the technical term for how much of you exists across all branches, quickly concentrates in branches where you're dead. The surviving branches become exponentially improbable. In some sense, you mostly die, even if some tiny fraction of you continues. Others argue that consciousness might not work the way quantum immortality assumes. Perhaps when the branches split, your subjective experience splits too in some sense, and the version that dies doesn't simply cease to experience, but rather experiences death in some way we don't understand. Or perhaps consciousness requires a certain threshold of brain function and coherence, and in many of the supposedly surviving branches, your brain is so damaged or disrupted that consciousness doesn't actually continue in any meaningful sense. The thought experiment also raises questions about personal identity. If the universe branches billions of times per second, with slightly different versions of you in each branch, then which one is really you? Is there a fact about which branch contains your consciousness? Or do all the branches contain conscious versions of you, each one equally valid? If so, then what does it mean to say your experience continues through the surviving branches? all your experiences. Continue through all the branches. The version that survives 20 quantum suicide trials is no more you than the version that died on the first trial. These are deeply philosophical questions that touch on the nature of consciousness, identity, and subjective experience. Quantum mechanics doesn't answer them. It just raises them in a particularly stark and troubling way. The mathematics of many worlds describes how quantum states branch and evolve, but it says nothing about what it feels like to be a conscious observer within that framework, or whether the concept of subjective continuity even makes sense in a branching universe. Despite all these caveats and concerns, quantum immortality remains a fascinating thought experiment because it takes quantum mechanics seriously and asks what it would mean for us, not just for particles. Most discussions of quantum mechanics focus on abstract systems or measurement devices, but we're quantum systems too. Our brains operate according to quantum mechanics at some level. The particles and fields that make up our neurons follow quantum laws. So whatever quantum mechanics says about reality, it says about us too. If many worlds is correct, then every moment of your life you're branching into countless versions. Most of those versions experience very similar futures because most quantum events don't have macroscopically different outcomes. But some branches diverge dramatically. In some branches you make different decisions, experience different events, live radically different lives. And all of these branches are equally real according to many worlds. Quantum immortality asks what this means from the inside. It's one thing to say abstractly that all branches are real. It's another to grapple with what that means for your subjective experience, your sense of being a single continuous self. If you're constantly splitting, if countless versions of you exist, if some versions die while others survive, then what are you really? A single thread of experience? A bundle of experiences across branches? Something else entirely? The thought experiment doesn't resolve these questions. No thought experiment could, but it forces us to confront them. It makes abstract interpretations of quantum mechanics personal and immediate. It asks not just what quantum mechanics says about the universe, but what it says about you, about consciousness, about survival, about what it means to be a person in a quantum world. Most people, upon first hearing about quantum immortality, have a strong intuitive reaction, usually negative. It feels wrong, or frightening, or absurd, but that reaction itself is interesting. It suggests we have deep intuitions about consciousness and personal identity that might not be compatible with certain interpretations of quantum mechanics. If many worlds is true, then our intuitions might be misleading us. Or perhaps our intuitions are pointing to something important about consciousness that quantum mechanics in its current form doesn't capture. Quantum suicide and quantum immortality will likely never be experimentally testable in the direct sense. We can't ethically perform such experiments, and even if we could, the results would be observer-dependent in a way that makes verification impossible. If you survive a quantum suicide scenario, you can't tell whether it's because you happen to be in a surviving branch or because the whole many worlds interpretation is wrong and you just got lucky. The experiment only tests something from the first-person perspective, and first-person perspectives can't be shared or verified. This makes quantum immortality fundamentally different from other quantum paradoxes. Most quantum paradoxes can be tested experimentally. We can perform the delayed choice quantum eraser, we can test Wigner's friend with quantum systems, we can demonstrate quantum pseudo-telepathy in the lab. But quantum immortality is purely a thought experiment about subjective experience. It can't be tested because the crucial question is what happens to your consciousness. And consciousness is not something we can measure objectively in the same way we measure particle properties. Nevertheless, the thought experiment serves a purpose. It highlights how strange the implications of quantum mechanics become when applied to consciousness and subjective experience. It forces us to think about what interpretations of quantum mechanics really mean when taken to their logical extremes. And it reminds us that physics isn't just about particles and forces. It's ultimately about reality, including the reality of conscious observers trying to make sense of their own existence within a quantum universe. Whether quantum immortality is a genuine implication of many worlds or a misapplication of quantum reasoning to consciousness remains debated, but the fact that serious physicists and philosophers have spent time thinking about it shows how profound and unsettling the questions raised by quantum mechanics really are. We're not just asking about particles anymore, we're asking about ourselves. From questions about consciousness, we turn now to questions about information and one of the most serious conflicts in all of theoretical physics. It's called the black hole information paradox, and it represents a direct collision between quantum mechanics and general relativity, our two most successful theories about how the universe works. Both theories have been tested extensively. Both make incredibly accurate predictions. But when you try to combine them in the extreme environment of a black hole, they contradict each other in a fundamental way. To understand the paradox, we need to start with what a black hole is. When a massive star exhausts its nuclear fuel, it can collapse catastrophically under its own gravity. If the star is massive enough, the collapse continues past the point where any known force can stop it. The matter gets compressed into a smaller and smaller region, until, according to general relativity, it forms a singularity, a point of infinite density where the laws of physics break down. Surrounding the singularity is the event horizon, a spherical boundary with a remarkable property. Inside the event horizon, gravity is so strong that nothing, not even light, can escape. Once something crosses that boundary, it's gone forever from the perspective of the outside universe. The event horizon is a one-way membrane. Things can fall in, but nothing comes out. General relativity describes black holes in remarkably simple terms. A black hole can be completely characterized by just three numbers: its mass, its electric charge, and its angular momentum or spin. Everything else about the black hole, all the details of what fell into it, the type of matter, the arrangement of atoms, the information content, becomes inaccessible. This principle is sometimes summarized by saying, black holes have no hair. They're bald, smooth, characterized only by those three numbers. This simplicity is elegant from a mathematical standpoint, but it creates a serious problem when you consider quantum mechanics. In quantum theory, information is sacred. It cannot be destroyed. This isn't just a principle we like. It's built into the mathematical structure of quantum mechanics. The evolution of a quantum state over time is described by unitary transformations, which are reversible. If you know the final state precisely, you can in principle work backward and reconstruct the initial state. Information is conserved. So what happens when you throw something into a black hole? Let's say you throw in a book. That book contains information, both classical information in the form of words on pages, and quantum information in the precise quantum states of all its atoms and molecules. According to general relativity, the book crosses the event horizon and is lost forever. The black hole gains a tiny amount of mass, but all the detailed information about the book disappears. The outside universe can no longer access it. This seems to violate quantum mechanics. The information was in the universe, then you threw it into the black hole, and now it's gone. But quantum mechanics says information can't just disappear. So where did it go? Is it somehow stored in the black hole? If so, where and how? The paradox becomes even more severe when we consider Hawking radiation. In 1974, Stephen Hawking discovered that black holes aren't completely black. Due to quantum effects near the event horizon, they emit radiation. Virtual particle pairs constantly pop into existence near the horizon. Usually these pairs quickly annihilate, but sometimes one particle falls into the black hole while the other escapes. The escaping particles constitute Hawking radiation. This radiation causes the black hole to lose mass very slowly. Over an enormously long time, a black hole will evaporate completely through this process. For a black hole formed from a collapsed star, the evaporation time is far longer than the current age of the universe, so this is purely theoretical. But the mathematics is clear. Black holes evaporate. Here's the problem. Hawking's original calculations suggested that the radiation is completely thermal, meaning it's random and carries no information about what fell into the black hole. It's like the radiation from a hot stove. It tells you the temperature, but nothing about what you're cooking. If the Hawking radiation is truly thermal, then when the black hole finally evaporates completely, all the information that fell in has been destroyed. The book you threw in is gone, not just hidden, but genuinely destroyed. Its information no longer exists anywhere in the universe. This is a direct violation of quantum mechanics. Information cannot be destroyed. But if the black hole evaporates and the radiation carries no information, then the information is destroyed. That's the black hole information paradox. General relativity says the information is lost. Quantum mechanics says it cannot be lost. Both theories are extremely well confirmed in their respective domains, but they can't both be right about black holes. This isn't a minor technical issue. It strikes at the heart of both theories. If information can be destroyed in black holes, then quantum mechanics is wrong in a fundamental way. The entire framework of quantum theory would need to be revised. But if information isn't destroyed, then either Hawking's calculation is wrong, which would be surprising given how carefully it's been checked, or general relativity's description of black holes is incomplete in some crucial way. Over the decades since Hawking identified this paradox, many solutions have been proposed. One possibility is that the information really is in the Hawking radiation, but in a very subtle and complicated way. Maybe the radiation isn't perfectly thermal. Maybe there are tiny correlations in it that encode all the information about what fell in. These correlations would be incredibly complex, scrambled across many particles, but in principle, if you collected all the Hawking radiation and had infinite computational power, you could decode it and reconstruct everything that fell into the black hole. This idea has gained support over the years. Calculations in string theory and other frameworks suggest that the radiation must carry information to preserve quantum mechanics. But proving this rigorously is extremely difficult. The encoding would be so complex that it's hard to demonstrate explicitly how it works. And there's a timing problem. If the information only escapes in the final burst of radiation when the black hole is nearly evaporated, it seems like it has to travel from deep inside the black hole to the outside, which would require faster than light signaling. But if it escapes earlier, gradually, then you run into other problems with how the information is distributed. Another proposed solution involves the holographic principle, one of the most profound ideas to emerge from studies of black holes and quantum gravity. The holographic principle suggests that all the information contained in a three-dimensional region of space can be encoded on its two-dimensional boundary. It's like a hologram, where a two-dimensional surface contains all the information needed to reconstruct a three-dimensional image. Applied to black holes, the holographic principle says that all the information about what fell into the black hole is somehow encoded on the event horizon itself. The horizon isn't just a boundary, it's an information storage surface. Every bit of information corresponds to a tiny area on the horizon. As things fall in, information gets added to the horizon. As Hawking radiation is emitted, information gradually leaks off the horizon and into the radiation. This is a beautiful idea that has become central to modern theoretical physics. It suggests that our three-dimensional universe might actually be a holographic projection from information stored on a distant, two-dimensional surface. Space might be emergent rather than fundamental. But while the holographic principle is appealing and has strong theoretical support, we still don't fully understand the mechanism by which information gets encoded on the horizon and then transferred to the Hawking radiation. Then there's the firewall paradox, a more recent twist on the information problem. In 2012, physicists Almheri, Marolf, Polchinski, and Sully argued that if information is preserved in Hawking radiation, then something very strange must happen at the event horizon. According to their analysis, to get the information out in the radiation while maintaining quantum mechanical consistency, the region just outside the horizon must be filled with extremely high-energy particles, a firewall. This would mean that anything falling into a black hole wouldn't smoothly cross the horizon as general relativity predicts. Instead, it would be incinerated instantly by the firewall. This violates the equivalence principle, a cornerstone of general relativity that says freely falling objects shouldn't experience anything special at the horizon. The firewall proposal trades the information problem for a different problem. It breaks general relativity in a new way. Many physicists find the firewall idea troubling and have worked to find ways around it. Some propose that the assumptions leading to the firewall might be too strong. Others suggest that the firewall only appears to certain observers but not to others, making it an observer-dependent phenomenon. Still others think the firewall is real, but there's a subtler way to understand it that doesn't quite violate the equivalence principle. Each attempted solution to the information paradox creates new puzzles. This is typical of fundamental problems in physics. When two deeply successful theories conflict, resolving the conflict requires new ideas, and those new ideas have to be carefully examined to make sure they don't create worse problems than they solve. Some physicists believe the information paradox is telling us that we need a complete theory of quantum gravity, a framework that unifies quantum mechanics and general relativity. String theory is one attempt at such a theory, and it has provided important insights into the information paradox. Loop quantum gravity is another approach. Others think we need something even more radical, perhaps a reconceptualization of what space and time fundamentally are. There's also speculation that the paradox might force us to reconsider what information means. Maybe quantum information doesn't work quite the way we think when gravity is involved. Maybe the rules of quantum information theory need modification in extreme gravitational fields. This would be a major revision of quantum mechanics, but if that's what it takes to resolve the paradox, some physicists are willing to consider it. What makes the black hole information paradox so important is that it's not just about black holes. It's about the fundamental compatibility of quantum mechanics and general relativity. Black holes are the testing ground because they're the places where both theories should apply and where both are pushed to their limits. But the lessons we learn from black holes should tell us something about quantum gravity in general. We can't directly experiment with black holes. We can't throw things into them and watch what happens to the information. The nearest black hole is thousands of light years away, and even if it were close, the timescales involved in evaporation are absurdly long, so we have to rely on theoretical reasoning, mathematical consistency, and thought experiments. Some researchers study analog systems in laboratories, things like sonic black holes created in fluids or optical analogues in materials. These systems have some mathematical similarities to black holes and might help us understand information flow in extreme conditions. Others study the mathematics of quantum field theory in curved space-time, trying to understand exactly how Hawking radiation emerges and whether information can be extracted from it. The black hole information paradox has been called one of the most important unsolved problems in theoretical physics. It's been studied intensely for 50 years and despite enormous progress, it's still not fully resolved. We've learnt that information probably is preserved, that Hawking radiation probably isn't perfectly thermal, that the event horizon probably encodes information in some holographic way. But the detailed mechanism remains unclear and controversies persist. What the paradox definitely tells us is that our understanding is incomplete. Either our description of black holes needs revision, or our understanding of quantum information needs extension, or both. Most likely, the full resolution will require a complete theory of quantum gravity that neither general relativity nor quantum mechanics alone can provide. That theory, when we find it, will probably change how we think about space, time, information, and reality in profound ways. The black hole information paradox is a reminder that physics is unfinished. We've built two magnificent theories, quantum mechanics and general relativity, and both work extraordinarily well. But they don't fit together seamlessly. Black holes are where the seams show, where the mismatch becomes undeniable. And until we fix that mismatch, we won't have a complete understanding of the universe. Every paradox we've discussed points to something missing in our understanding, but perhaps the most fundamental mystery of all is the one that started the whole quantum revolution and remains unsolved to this day. It's called the measurement problem, and it's about the most basic question you can ask. What happens when we look at something? In classical physics, measurement is simple. You have an object with definite properties. You design an instrument to detect those properties. The instrument interacts with the object, and you read the result. The object had those properties before you measured. The measurement just revealed them. Looking at something doesn't change it, except perhaps by disturbing it slightly in predictable ways. But quantum mechanics doesn't work like this at all. Before measurement, a quantum system doesn't have definite properties in the classical sense. Instead, it's described by a wave function, a mathematical object that encodes probabilities for different possible outcomes. The system is in a superposition, existing in multiple states simultaneously. An electron isn't at position A or position B. It's in both positions at once, with different probability amplitudes for each. Then you measure it, and suddenly you get one definite result. The electron is at position A, let's say. The wave function has collapsed from a superposition of many possibilities to a single actuality. This collapse is instantaneous and discontinuous. One moment the electron is spread across space, the next moment it's localized at one point. The mathematics of quantum mechanics describes this process in two very different ways. Most of the time, quantum systems evolve smoothly and deterministically according to the Schrödinger equation. The wave function changes gradually, and if you know it at one time, you can calculate it at any other time. This evolution is reversible and preserves information. It's called unitary evolution, and it's how quantum systems behave when they're left alone. But measurement is different. When you measure a system, the wave function doesn't evolve unitarily. It collapses, jumping suddenly to one of the possible outcomes with a probability given by the wave function. This collapse is not described by the Schrödinger equation. It's a separate process, often called the collapse postulate or the Born rule. And it's fundamentally different from unitary evolution. It's not reversible. Information about the other possibilities is lost. It's random, or at least appears random. This dual description is strange. Why does the wave function sometimes evolve smoothly and sometimes collapse discontinuously? What determines when collapse happens? This is the measurement problem. Quantum mechanics gives us two different rules for how systems behave, one for when they're not measured and one for when they are. But it doesn't tell us what counts as a measurement or why measurement is special. You might think measurement just means interaction with a measuring device. but measuring devices are made of atoms, which are quantum systems. Why should they cause collapse when they're quantum systems themselves? If you include the measuring device in the quantum description, then the combined system of particle plus detector should evolve unitarily, not collapse. But we don't observe superpositions of measuring devices. When we look at a detector, we see a definite reading, not a blur of possibilities. So maybe the collapse happens when a human observer looks at the detector. But humans are made of atoms too. We're quantum systems. Why should we be special? And what about experiments that record results automatically without human observation? Do those results exist before someone looks at them? These questions have divided physicists since the birth of quantum mechanics. Different interpretations give different answers, and after nearly a century, there's still no consensus. Let's look at the major interpretations and what they say about measurement. The Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg, is perhaps the most famous. It says that quantum systems don't have definite properties until they're measured. The wave function isn't a real physical thing spreading through space. It's a mathematical tool for calculating probabilities. When you measure, the system interacts with a classical measuring apparatus, and this interaction produces a definite result. The wave function collapses because you've gained information about the system. Copenhagen is pragmatic. It tells you how to calculate experimental results, and those calculations work perfectly. But it leaves fundamental questions unanswered. What exactly counts as measurement? What makes measuring apparatus classical? At what point does the quantum realm end and the classical realm begin? Copenhagen doesn't provide clear answers. It essentially says, don't ask what's really happening, just calculate probabilities and do experiments. Many physicists found this unsatisfying, which led to alternative interpretations. The many worlds interpretation, proposed by Hugh Everett in 1957, offers a radically different picture. It says the wave function never collapses. Ever. Instead, all possible measurement outcomes occur, but in different branches of the universe. When you measure a particle's position, the universe splits into multiple versions. In one version, you see the particle at position A. In another version, you see it at position B. Both versions are equally real. You just experience one of them. Many worlds removes the measurement problem by removing collapse. Everything evolves by one rule, the Schrödinger equation. There's no special moment of measurement. What feels like collapse is just you experiencing one branch of a splitting universe. It's elegant, but demands believing in endless parallel versions of you and countless branching realities. Many find that excessive. If all branches exist, why do we only experience one? Pilot wave theory, Bohmian mechanics, says particles always have definite positions, guided by a quantum wave. The wave never collapses, it just directs particles along set paths. It restores realism and determinism, but the guiding wave is non-local and unobservable, which makes many physicists uneasy. Relational quantum mechanics says quantum states are only defined relative to observers. There's no universal wave function. Collapse isn't physical, it's just a change in what an observer knows. Reality becomes a network of relationships, not absolute states. Objective collapse theories say wave functions really do collapse on their own when systems get big enough. Collapse is physical, not subjective. But they must introduce new constants. How often collapse happens, what size triggers it, and we haven't detected these effects yet. Consciousness-based interpretations claim collapse occurs when awareness enters the picture. Only observers with minds turn possibilities into definite outcomes. Most physicists reject this because it mixes physics with philosophy and raises endless questions. What counts as conscious? Do animals collapse wave functions? Do computers? None of these interpretations has won. The math of quantum mechanics works perfectly, but the meaning remains open. The measurement problem still matters because it shapes how we think about reality, causality, and whether outcomes are chosen, branched, or observed into existence. Until we understand what actually happens during measurement, our picture of reality is incomplete. Quantum mechanics gives us extraordinary precision and technology, but not a clear story of what's real between observations. That mystery is why the interpretation debate refuses to die.